Okay, so hello everyone. My name is Tim Dudgeon from Informatics Matters. I'm going to talk today about Fragnet Search, which is our implementation of the Fragment network tooling that was first described by Aztecs and is used in their fragment-based drug discovery programs. And what I'm going to describe is some work that was done initially at the Diamond Light Source as part of their fragment screening program. But that work has been extended by us, Informatics Matters, and the Fragnet Search application, an API that I'm going to demonstrate here is the outcome of that. So firstly, a little bit about chemical search and particular similarity search. Everything I'm going to do today is available on the Fragnet Search website, which is fragnet.informaticsmatters.com. And in the documentation, there's various information here, far more than I can go into in the time we have here. But one of the key things I want to start with is chemical search and similarity search. So traditionally, that two approaches you can use. One is substructure search, which works well, but you need to define a specific substructure. And then there is similarity search, which is based around chemical fingerprints and some measure of distance between those fingerprints, typically a Tanimoto distance. Now, whilst the similarity search works reasonably well for big molecules, when you're talking about fragments or building blocks, which are very, relatively small molecules, this traditional similarity search really doesn't work very well. And the reason for that is that the number of bits set in the fingerprint is very low, and you get a very low signal. That means it's very difficult to really identify similar compounds. If you lower the similarity threshold, you very quickly get into the noise, and you don't get a good distinction between what are really similar molecules and what is background noise from the fingerprints. And also, the results of this are not necessarily chemically intuitive. It's more like this: if the computer says yes type answer. It isn't really a chemist's view of similarity in many senses. What Fragnet Search does is, by using fragmentation as the way of traversing between similar molecules, you get a much more chemically intuitive answer. As someone said to me who uses this, it thinks the way I think. So it thinks the way the chemist thinks. So what is the basis of this fragment network? Well, that's described here in the About document. And I'll just go over this very briefly. There's a lot more information here on the website. And if you want the full details, read the Aztecs paper, which is linked here, that really describes the methodology in detail. I'll illustrate this using the prototype molecule that Aztecs use, which is 4-hydroxybiphenyl. The process of generating the fragment network data basically breaks this molecule up into its fragments at the entry points of rings. So where you've got a ring and a functional group of a ring, you basically split the molecule up into fragments. And so the 4-hydroxybiphenyl gets split into these three fragments: the top ring, the lower ring, and the hydroxy group. You then recombine those fragments in an all but leave out one method combination, and you generate the child molecules, which are then fragments of the parent molecule. And in this case, we end up with 4 different child molecules. You can then recursively fragment those molecules further, and you get a pattern like this down to the individual fragments that cannot be further fragmented. And if you cut out the intermediary fragments, this is the fragment network that gets built from this 4-hydroxybiphenyl molecule. You'll see we've got biphenyl, we've got phenol, we've got the 2 rings, and further fragmentation goes down to things like the hydroxyl group and the benzene ring and things like that. Now, that's the fragmentation pattern for this particular molecule, but as you fragment additional molecules, you obviously get common fragments between them. And that then allows you to traverse the fragment network from one molecule through a child molecule, or actually a parent molecule, and then on to a different molecule. And these traversals, these what you can call hops between the nodes in the fragment graph, is what you use to determine the similarity. We'll see this in action in a minute. And what this allows is to find neighbors based on the fragment network. So here, this chloro substituent is clearly a superstructure of the original 4-hydroxybiphenyl. That is a one fragment deletion of, if you delete the chloro group, you get the 4-hydroxybiphenyl. That's a one-hop transformation. In this molecule here, we've got a 2-hop transformation because we've got 2 substituents. To go from the 4-hydroxybiphenyl, you need to add a methyl group at this position, and you need to add a chloro group at this position. So the number of hops will generate you more complex molecules. But using 2 hops, you can also do a substitution. You can remove a fragment, in this case the hydroxyl, and then replace it at the same position with another substituent. So you can get substitutions. And you can also replace rings, so you can do ring substitutions. So whilst some of these molecules would be found by classical similarity search, some of these more complex ones definitely wouldn't be. The similarity scores for these would be well down into the noise. And so that's the theory of it. The process of generating the fragment network is quite complex because the fragmentation can be quite extensive. The simple example we just saw was a fairly minimal example. What we do is we start with vendor files, such as ones from Mulport or Edamine or whatever. We then standardize those molecules so they're all present in a single standard representation, independent of how the vendor described it. And then from that standard representation, we fragment and then we deduplicate. We have to deduplicate because of the fragmentation processes going on in parallel across a number of servers. And then once we've got that fragmented data, we then augment it, which means adding back in information from the vendor, such as the vendor's ID or maybe pricing information and things like that. And then from that, we generate data at other nodes, which are basically the molecules in the fragments, the relationships, those are the parent-child relationships between the fragments. And we load that data into a Neo4j graph database that allows us to search it. And we've done this for a number of data sets, some of which are listed here. For Mulport, which has about 7.5 million compounds, we end up with over 100 million nodes. So that's the original molecules plus the fragments of those molecules, and about 600,000 edges. For bigger libraries, such as the subset of enamine real that is used at the Diamond Light Source, we start with 39 million, or nearly 40 million compounds. We have 191 million nodes and over 1 billion edges. So there's a large amount of data here. It does take a lot of computational power to process it. But once you processed it and got it into a Neo4j database, you can search it very fast and very efficiently. So let's see this in action. So if you go to the fragnet.informaticsmatters.com and then log in, you'll be presented with this query page. And there are a number of example molecules here which we can use, but obviously you can just sketch in your own molecule. These query parameters are very important. The heavy atom count is the difference in the number of heavy atoms between the query molecule and the target molecule. So any molecules that are bigger or smaller than 3 heavy atoms compared with the query won't be included in the results. Similarly with the ring atom count, that's the number of atoms in rings. And the number of hops here is what we saw in the Fragnet network, how many traversals of the network. Let's keep this simple to begin with and just go for one hop transform. And when we get the results, you see that the results are grouped based on the type of transform. Here is the first one where there is an addition at this position, and in this case, this is the only addition, the only addition at that position in the database. Here's another addition at a different position. Here is an addition onto the benzene ring at the sort of meta position, and you see 4 different variants here that are available. Now, with one hop transforms, we're only going to see single additions or single deletions because it's a one hop transform. If we now go back and rerun this query, but with 2 hops, you get a much wider diversity of results. You obviously see the same ones we had before, but and so these are additions, 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 and here we have one that is additions, plural. So here you're seeing double substitution, a double addition, adding something at this position and something at this position. And go down further, we've got more additions here at different positions, but more interesting as we get towards the bottom here. Here we have so ring substitutions. So in this case, we've removed the ring that was there originally and replaced it with a different ring. So here you're getting some quite diverse molecules, but they're clearly related in chemistry to the original one. And what you'll notice, we actually report out a number of optional parameters which you can actually specify if you go to the settings, what to calculate. By default, we just specify the log P and the similarity score based on Morgan 2 fingerprints. But that similarity score, you'll see, is really quite low. It's down in the 0.3 regions for some molecules, maybe even lower for others. These are very unlikely to be found by similarity search because that's well down in the noise region. But the Fragnet search can easily identify them and group them according to type of transform. So here's another type of ring transformation, this time when we're changing the benzene ring for other rings. And that's fine. Here's another one. Another type where it's the linker between the rings that is being substituted. So if you remember, the original molecule was just linked by an amine. Here we're changing the linker. In this case, just a single bond. In this case, changing it to a methylene group, etc., etc. So again, we've got quite diverse, but clearly chemically similar. According to a chemist's sense of the word, these molecules would be considered similar, but according to similarity search, they may not be. Now, once we've got our molecules here, what we can do is we can start picking them and say, I want these for purchase. So I'm just adding these now to my shopping cart. So I'll add those 3. I'll go back. I'll run a different query. Maybe I want to add some results from this query. And once I've gone through all that, I can now go to my shopping cart, and I've got the molecules that I've just picked, and maybe some actually I had picked earlier as well that are already on the cart. I can now go and fetch the availability of those compounds from the database. And it goes back and fetches the actual molecules that are provided by the suppliers. You can filter the suppliers. We'll show all of them. And so here we're getting the molecules that were actually specified by Molport and by ChemSpace. And we can now go through and make a choice as to which ones we want to actually go and purchase. In this one, I've chosen the ChemSpace one, not the Molport one. I'll have that one. I'll have that one. This one, I'll have that one. So you can easily just go through and cherry pick the molecules you want. And then at the bottom of the page, you then have the list of identifiers that you have selected. You can also, if you want, you can have the identifiers plus the smile strings. But we're going to just take the identifiers. What I'll do quickly here is just limit this to the ChemSpace ones. Now let's assume I want it to go to ChemSpace and order those compounds. So I just copy those identifiers, and then I go to ChemSpace go to the ChemSpace website, go on the chemical search section, go to text search, and then paste in those those ChemSpace identifiers, and then search. And now we're into the ChemSpace purchasing system. We can go and order these molecules. We've got information about the pack sizes and the prices and things like that, and we can further filter and go on and make a purchase. We are planning on making a more direct link into the ChemSpace and other vendors' procurement systems to make this process a little bit easier. But you've seen it's really relatively simple to pick your molecules and then go to the vendor and purchase them. So basically, that is the Fragnet Search application itself. As I said, there is plenty of documentation on the theory behind it and on user documentation on how to actually use it and things like that. But what I'll move on and show you now is how you can use this from the API. One of the real advantages of this compared with things like substructure search and similarity search is that it is much more amenable to automation. So if you've got a workflow where you've got some compounds and you want to expand them out into a set of similar compounds, with substructure search that's very difficult because you'd have to run a whole series of substructure searches really to get coverage of the diversity you want, and that's a very manual step to actually devise those substructure searches and to execute them. It's not amenable to automation at all. Similarity search you can automate, but you've really got the problem of what threshold to use to limit the number of searches and to make sure you get real molecules, not ones that are down in the noise where you get flooded by thousands and thousands of molecules. With Fragnet Search, it's really very simple. You just got those parameters, the heavy atom count, the ring atom count, and the number of hops. This is very amenable to automation. If you want to automate it, you obviously don't want to be clicking buttons in a website. What you want to do is be using it from an API. And so the API behind this Fragnet Search is available through an API, and also another API, which we call an expansion search, which is probably more suitable for this sort of use. And this I'm illustrating using a Jupyter notebook, but basically it's just a REST API. You can call it from any programming language you want, which makes it very easy to install to integrate into your own applications and your own workflows. So I won't go through this in detail, but in just the key bits. Firstly, you need to authenticate, so you need to you need to enter your username and password in order to get an authentication token. And then once you've got that token, you can then just run the search, which is basically calling the REST API with the query molecule, parameters for the number of hops, the heavy atom count, the ring atom count, and then you call the URL, and you get passing in the token, the authentication token, and then you get back the results. And the results are some JSON. It shows you the actual query that was executed against the graph database, and it gives you a whole series of results. So the members are the actual molecules that came back that are similar to your starting molecule. And you get the smiles, and you get the compound IDs from the different vendors. This particular version is running on the OpenRiskNet site, where we've got Molport, ChemSpace, and ToxCast data loaded in. So you'll see identifiers for for these molecules. So that once you've got this JSON, you can then obviously extract out the smiles and then go and do further things with it. And obvious use of this could be in a toxicity reduction program. You had a molecule that had some toxic liability. You wanted to identify some similar molecules that might retain the activity, but would lower the toxic profile. So what you might do is you take your molecule, you'll use the Fragnet Search API to expand that molecule out to a whole series of candidates that you might then want to test. You might want to put through your tox model or your activity models and try to work out, I'd try to identify in there molecules that had a better profile than your starting molecule. So that's basically it. It's very easy to use this, both the UI and the API, and I think it provides a very quite novel alternative to a very thorny problem that's been around for a long time, and that is getting effective chemical similarity, particularly among small molecules. So with that, I'll finish. Just a reminder, the site is fragnet.informaticsmatters.com. In order to access it, you need to have an account set up. So contact us on info.informaticsmatters.com if you want to have an account. At the moment, we're in evaluation mode. Before too long, we'll be switching to a subscription basis and we'll probably be doing that early in the new year. But at the moment, it's free to use while we're in the evaluation phase. So that's it.